Alright, time for another DraftPhysics.com, DebatePhysics.com, also video presentation. So this is the Veritasium video on rainbows, and it's just basically the hype that somehow he has once again, revealed some truth that has been hidden and we all don't understand, and blah blah blah, and it's just a bunch of crap. Okay, there's no new physics here, just him pretending he's, in some way changed the physics. And no, it's the same Newtonian physics. And frankly, and all of their interpretation of it is all wrong. And all of the interpretation certainly that goes astray from Newton's interpretation, which wasn't about a bunch of waves. Anyway, so this part where he's, got a little crystal ball and is pretending, nobody thought of any of this stuff before, and you could sort of argue that Newton was kind of famous for being very good with glass and lenses and such. But anyway, you can look it up online, using a sphere, glass sphere to create rainbows. I mean, it's just not. It's not new. Yeah, no. It's kid science, frankly. Anyway, so I mean, it's just the hype part. It's just so irritating. And so the first part was really about the distinction between particles and waves, and why light moves slower through mediums. And I provided the rational explanation in contrast to their made up bullshit that doesn't really answer the question with a mechanism of how, beyond just, stuff they say. So we'll go back a little bit to be fair here. So he's just talking about the fact that, the rainbow is made by the fact that light is concentrated, essentially, by angles that run out, because there's the circle isn't infinite, so it has a finite number of angles in it, and some of them end up compressed, and that's essentially why you see a rainbow, is because you can see more light, and that there would be bows in other places if enough light could hit those places, but it doesn't happen, so you don't see anything. Alright, pretty much. So we'll just play the rest of it just to be fair, but it's not very interesting, so watch at your own risk of wasting some valuable time in terms of neuron exercise. You might not get much out of it. And I might end up having to be just redundant in pointing out how it's not a wave, it's particles. Particles explain it, vectors explain it. All of this is just geometry of energy. Straight line geometries explain it all. No need for anything called a wave. And such. So I have to just change the volume here, and we should be ready to go. And such. I think this is an okay location to start. I don't know. It doesn't really matter where I cut off.
Only the difference in maximum scattering angles and the caustics they produce that gives us the rainbow.
So the caustic is the constant.
So now we know what happens along a single radius of the sphere.
So anyway, so the caustic is where the angle gets too slight to make differences. So the differences of the angle, it's sort of like the pendulum argument for doing kinetic energy experiments. The motion at the bottom is really inexpensive. It's really easy to create motion down here. When you're starting to add motion in the upward direction, that's where it gets expensive. That's where you're pushing against gravity. So down here, not much push up against gravity. Up here, lots of push up against gravity. So it's sort of the same rule for all spherical experiments, are going to run into this idea that your angles change dramatically from 0 degrees to 90 degrees, and there's a consequence to that change. Yeah, depending on your orientation, there'll be less and less change in what's going to happen, whether you're going towards the end of the base or the other end. There's going to be where every inch matters, and then places where every inch doesn't matter. Same thing happens with this double slit experiment. If you could extend the double slit pattern, the nodes of the fringe pattern get very large here, and they get smaller and smaller and smaller as they go up. So you can sort of understand that the same effect is creating a gigantic covering an awful lot of space. The photons are landing with the same energy on a much larger area, and that's part of the experiment. All right. What do I want to do? Something else I wanted to finish here. Where's this? I have this video somewhere, like here. Okay, so now I should be able to turn it on and off a little more coherently. And so leave us continue.
So what happens if we uniformly illuminate the whole sphere with white light? Well, I blacked out my window and cut a hole just big enough for afternoon sunlight to cover the sphere.
So, I mean, he deliberately has a bunch of graphics from the 3 brown, 1 green guy or whatever, but he doesn't just go on Google and find 500 little videos where they show very clear rainbows created by, round glass spheres, transparent spheres. So, it's an experiment that's been, done lots and lots of times. He just shows somebody else doing it very well, instead of kind of trying to prove that he does it better or something. Or like I said, I would assume Newton did this, and this is exactly why Newton knew what angles all this crap happened at. I mean, this is probably Newton wasn't the kind of stand in the rain kind of guy. It wasn't Benjamin Franklin.
You can see there's a circle of white light coming from the reflections off the back of the sphere. And then around it, there's a ring of rainbow colors.
Come on! One raindrop creates a cone of light. The inside is all white, and the ring around the outside is colored. This is the perspective of a rainbow from a single raindrop. All these different light rays coming in at different places reflect back off the front surface and the back surface, and that reflection off the back surface reaches a maximum angle. And for blue, green, yellow, and red, the maximum angle is different. So the red maximum angle is the furthest. That's why it's on the outside here. So good. So good.
Yes. So not profoundly new information. No.
What I really wanted to see is if I could observe the cone of different colored caustics that produced that ring.
So he's saying, so he wants to look into like a double slit experiment and say, well, can I see it? Yeah, of course you can see it. If it's projected on a wall, you can see it by looking at it. Yes.
You've got to see this color cone. You have got to see this. My eye is right in the color cone here. I can see the color cone. That is so cool.
Yeah. Whoa. No, sorry.
So this is the crazy focus on the back.
Yes, you can already tell it's a magnifying glass essentially, and so yes, it's probably a hot place right there.
Of the sphere. If you stick your finger in there, it gets burnt very quick. Ow! This thing is a focal.
Now, this really looks like a rainbow, but remember, this is just the light coming away from a single droplet. When you see a rainbow, there are billions of...
Right, but you're the focus of all of them, so, from your perspective, it's just for you. But obviously, you could just move you to a different location to see exactly the same thing. Just like if, for example, photons go through a bunch of, ionized crap around a sun, for example, and you can see the light from a planet or a sun, I mean a star, and you'd be able to see it from any location. You could go anywhere and it would look bent.
Raindrops, and each one is projecting a rainbow cone back toward the sun. So how does all of this create a single unified rainbow?
Well, because they're all obviously, okay, you're the focus. You can't see the rainbow they produce unless you are the focus.
Well, for your eye to see a color, let's pick red, in a certain part of the sky, then the red caustic from a raindrop there must go directly into your eye. And this only happens when the angle from the sun to the raindrop to your eye is 42 degrees. And this explains why rainbows take the form of an arch with a 42-degree angle.
Right, so you already demonstrated that they really are taking the form of a circle, just that the other half of the circle's going through the earth, and so you don't see it.
Now, the violet light from these same raindrops passes above or beside your eye, so you can't possibly see it. But there are raindrops below and inside the arc of those red-giving raindrops whose violet caustics do intersect your eye. They form a shallower angle of 40 degrees between the sun and your eye. And of course, there are raindrops at all intermediate angles that send you all the other colors of the rainbow. So a rainbow really is the ultimate optical illusion, from billions of droplets, each projecting a rainbow cone.
So I don't know why it's exactly called an optical illusion, because, I mean, the real photons, they're really being bent by reflecting off surfaces at angles. Why is that an illusion? I mean, is it a mirror or an illusion? I don't think so. So I'm just saying, it's not really an illusion, let alone the ultimate illusion.
You see a single static arch of color, but the droplets sending you those colors are constantly changing. A single drop as it falls might send to your eye first red, then orange, yellow, green, blue, indigo, and violet. And because a rainbow must form an angle of 40 to 42 degrees...
All right, well, that even sounds a little suspicious, frankly. All right, back. Continuing and such. Yeah, I thought we were continuing. What is this? Computers. I don't understand. Is the sound off for some reason? I don't know why. Okay, now continuing. I gotta hit this button.
That passes from the sun through the back of your head. So your shadow is the center of your rainbow. This means no two people can ever see the exact same rainbow. In fact, your left and right eyes don't even see the same rainbow.
So, yes, and that's true about everything on Earth, though. Come on, every single thing I see, my eyes are seeing different photons, so I can't see the same photon in both my eyes. So, yes, we all see everything different, but the point is that this is one of those systems that's producing exactly the same thing, frankly. So what you're going to see is going to be exactly the same thing. So it's just I mean, it's technically true, but not very meaningful.
A rainbow is an optical illusion.
No, it really isn't. So I guess I'm just arguing. It's really not an optical illusion, frankly, in the sense that everything is an optical illusion. Everything is made out of all kinds of nuance of photons coming from different directions, reflecting in different angles. So, I mean, come on.
Made unique for each perspective. This also explains why in most parts of the world you can only see a rainbow in the early morning or late afternoon.
I don't know why that explains it, but obviously that part, the unique part, doesn't have anything to do with the morning or the late afternoon. That just has to do with the angle thing. It's a small angle, and so, yeah, it's just not likely to happen unless you're in a very tall tree or something. I don't know.
Not in the middle of the day. The higher the sun is, the lower the top of the rainbow is.
Right, so if you're looking over a cliff or you're up and, so if you're looking down at like a waterfall, you can see one. So there are other ways you can see one, but,
And when the sun is more than 42 degrees above the horizon, no rainbow is visible from the ground.
Right, there's one there, see, so. Yes, so you can't see it if you're looking up or straight across, but you can if you can look down.
But even when rainbows are visible, you can turn them invisible using sunglasses. That is, as long as they are polarized.
All right, so again, the fact that the light's polarized, I don't know, is that terribly interesting? I don't know.
Light from the sun is unpolarized, which means the electric fields of the light are all randomly oriented, oscillating back and forth equally.
So they're not oscillating, so that's just the word, just totally unnecessary. Polarization's a real thing. The photons, the bits, the composite that makes up a photon. And he could point out that the actual composite that makes up a photon is much bigger, than an electron. So obviously it's a rather large object, many atoms across the polarization. So clearly photons don't interact with single electrons. They act on atoms, a collection of atoms. That's how you detect one.
In all directions.
A single atom could only break a photon. It can't itself make one.
But it just so happens that when the
I'd argue that single statement is probably a better insight than the entire video. It's just recognizing that a single electron can't produce the phenomenon of a photon. It can only make a contribution to an event that will be a photon.
the light in the rainbow ray reflects off the back of the droplet, it does so very close to a special angle known as Brewster's angle. At this angle, all light with its electric field oriented parallel to the plane of reflection is transmitted, so it passes out the back of the droplet. And therefore, the only light that is reflected has its electric field perpendicular to the plane of reflection.
So, the only light that is reflected is perpendicular to the plane of reflection. Alright, so that's an internal reflection. So that's equal in, equal out. So that's not the one getting distorted. The one that goes through is the one bent. Gotcha.
This is the light that creates the rainbow. This means rainbow light is polarized along the direction of the rainbow, so horizontal at the top and closer to vertical on the sides. This is why you can use a polarizing filter to make a rainbow disappear, or to make it brighter if you orient the filter to allow that polarized light to pass through.
Alright, so I don't think there's any way you can make it brighter, so I don't think that was true. So I think that's wrong.
But why is it brighter under a rainbow than above it? Well, this is because the raindrops beneath the rainbow are reflecting.
Yeah, they're also trying to be rainbow, but they just don't have enough photons to do it. So the reason why you're seeing the bow is because that's where a whole bunch of photons all go to the same place. And the rest of the space, not so much. So they would be making a rainbow if there was enough photons to make the rainbow, but there's not. So it just makes it a little brighter.
Reflecting all colors of light at you off their back surfaces. This is what created the white disk in my glass sphere experiment. In contrast, the raindrops above the top of the rainbow are not reflecting any light to you off their back surfaces. Your eye is now outside the maximum deflection angle of all of the colors. But if you look up even further, sometimes you see a second, fainter rainbow with its colors inverted.
Alright, so I got a good picture of one of those too. Anyway, so that's just a third reflection. So the light's just reflecting again.
Double rainbow!
So where does this come from? Well, it comes from an additional reflection inside the raindrops. Now, instead of reflecting once off the inside of the sphere, light reflects twice. These reflections also create colored caustics, though much fainter because light is lost with each reflection. If you look at deflection angles, this light starts going out the back of the raindrop, so at an angle of 180 degrees, but the further out light hits from the center, the smaller the angle light reflects back at, until it reaches a minimum of around 50 degrees for red light. Then it turns around and goes back the other way. So between 42 and 50 degrees, it is dark because no light reflected once or twice inside a raindrop comes out at this angle. This is known as Alexander's dark band. Now, there is photographic evidence of third and fourth order rainbows formed after 3 or 4 internal reflections. But this light comes out the back of a raindrop, so they are the only kinds of rainbows that you could expect to see when looking in the direction of the sun. But they're so faint that conditions would have to be perfect. Under lab conditions, up to 200th order rainbows have been detected. But that is not what is going on here. This is known as a supernumerary rainbow. Multiple rainbow-like bands show up under a primary rainbow. But this only occurs when the raindrops are all really small, just tenths of a millimeter in diameter. Now the light rays that pass just above and below the primary rainbow ray end up coming out at similar angles under 40 degrees, but they travel slightly different distances on the order of a wavelength. And because of this, those light rays can interfere constructively and destructively, producing a series of light and dark bands inside the main rainbow. Different colors in these supernumerary rainbows.
In phase, out of phase. Again, not complicated. No destructive interference necessary. It's just that the distances do, like I said, is a wavelength of difference. Then you're going to get a out of phase, in phase, out of phase, in phase.
Overlap more than in the main rainbow, so they can produce strange colors like magenta, a combination of blue and red.
Supernumeraries also offer a clue to how these small rainbows work. Whenever I saw images like this, or even observed this sort of thing from an airplane, I wondered how a rainbow could be so small.
These are known as glories or Brockenbows. Instead of the usual 42 degrees, these circles of color are only around 2 to 4 degrees wide. Well, the key is that just like in supernumeraries, glories are due to interference, so they too require tiny water droplets, just tenths of...
So you probably can't see them at a distance. So if they were at a distance, then maybe they'd be much bigger. So again, it's another who knows.
...of a millimeter in diameter. These are the sorts of droplets you'd find in fog or clouds.
Light that strikes the edge of the drop can go around the back and come straight back at the source. You can see that with the laser on the glass sphere. But effectively, in the presence of...
It doesn't really do that, though. It reflects internally to do that, not externally, but whatever.
Parallel light rays, tiny little droplets become a ring source of light. But for these tiny droplets, the distance from one point to all edges of the sphere can vary on the order of a wavelength. So take, for example, the point right out in front of the drop. Well, now the distance to all edges is the same, so the light interferes constructively here and produces a bright spot. But a little bit off to one side, and now...
So this is essentially illustrating the double slit, and you can just point out how, well, obviously the wave centers would have to be here and here, the two nodes that it's coming off of. And then you have to explain how those could be the wave centers in, say, a slit experiment or something like that, because that's not... If the wave was coming through the surface, through the opening, then the wave center would be in the middle of the opening, and that math won't get you the right answer. So obviously the photons and the material can't be coming from that location. It has to be coming from one of the surfaces. So it's kind of a slam dunk evidence that the slit experiment really is about two surfaces. So in a way you could just look at this and say, they say in the single slit that the wave is coming out of the opening. when no, the wave is on one side where the surface is and where the other surface is. Those are the point sources for the scatter.
Now, half of the light, on average, has traveled an extra half a wavelength, and so we get a dark spot here. If you go a little further, well, now the light has traveled an extra whole wavelength, so now the light is arriving in phase again, and we get a bright spot here.
Not very visible, frankly. So that graphic didn't work very well. It's just wrong to imply that it has to do with interference when it just has to do with phase. In phase, out of phase.
So we can rotate this around 360 degrees and extend it out in all directions, and what we get is a fuzzy bullseye pattern. And of course, all the different colors of light have different wavelengths, and so these bullseye patterns aren't completely overlapping. So when they're superimposed, what we see is rings of color. Now, this is just the pattern from a single droplet, but just like with a rainbow,
I think they are overlapping, so I think they all overlap completely consistently, so they all have the same center, and they just have different size rings, so, yeah.
If you have millions or billions of these droplets, they all contribute to produce this same pattern with your shadow at the center. And it was just such a pattern that inspired a Nobel Prize-winning discovery. In September of 1894, a scientist named C.T.R. Wilson was visiting an observatory in the Scottish Hills. It was then that he observed the colored rings surrounding the shadow cast on mist or cloud. He recalls that these glories greatly excited my interest and made me wish to imitate them in the laboratory. So Wilson invented the cloud chamber for the explicit purpose of observing glories. Of course, once he discovered the cloud chamber made the tracks of energetic particles visible, he abandoned his original aim and was later awarded the Nobel Prize. But it all started with the mystery of rings of color in the fog.
Yeah, it really has nothing to do with the subject. But yes, interesting factoid, I suppose, that a lot of discoveries are made accidentally. And, maybe that's not a good sign, that physics doesn't intentionally know where the good places to look are.
Oh, that looks so nice.
How did you see that? So now,
Baby talk.
now I hope you know, my son, why rainbows are curved and why they're polar.
So, again, I don't know if he really went into the whole curvy thing too much, frankly, so, but whatever.
Polarized and why they exist at all. And even more than that, I hope you know why I find such enjoyment in learning about our...
Oh, brother, you're a preacher. You don't find any enjoyment in learning, frankly. You are totally unresponsive to critique, and, again... Are you going to teach your kid that it's 1/2 mv squared, even though you have zero evidence that that's true? Are you going to tell him it's, hey, it takes 100 times the fuel to go 10 times faster. So remember that. Get a really slow car. Because, boy, you'll use up so much, you'll waste so much energy if you drive fast. Science says. Yeah, you're going to do that? Yeah, these people are just such liars. You're going to tell them when you weigh twice as much, you somehow have 4 times the energy? Just sitting in a chair? Just so bad. All right.
world.
And then he does this commercial for Brilliant that's just so, cringeworthy.
Why it is worth figuring things out. For millennia, rainbows have been this blatant challenge held up to us by nature.
So again, the challenge was Newton slam dunk. I mean, just amazing figuring.
But can you figure this out? And it's satisfying to say, we have.
Oh, brother. 300 years ago.
I'm looking at a different rainbow than you.
It's true.
So he's taught his kid to just mimic what he says.
When I started researching this video, I thought I already knew about rainbows. I mean,
Yes, well, it turns out that, yes, you didn't add anything new, so...
I'd learned all of the colors of the rainbow in school and that it was caused by light refracting and reflecting, but I realize now that I'd only really just memorized things about rainbows and not really understood how they work.
So that seems kind of weird, just because, frankly, if you know there's angles and it's reflecting, I mean, what else is there? There's nothing else to the story.
Learning should be about mastering a subject, not memorizing a list of facts.
Yes.
And that's why we asked Brilliant to sponsor this.
We asked them, we pleaded with them, please, please. Oh, it's so disgusting. Eek. God, I hate this planet. Hate it here. Just, you people suck. Alright, so that's enough of that shit. Ugh. It's just such shitty science. This fucking show science. Yuck. Anyway, till the next time and such and so forth and whatnot. I warned you, this wasn't going to be a bing bang bong kind of video, but whatever. Till the next time and such.